Reuben, Holmes, thanks so much for joining me today.
Thank you for inviting me. It's a real privilege.
Yeah, so you're a plant chemist at National Nuclear Laboratory, and you're calling out of the UK.
That's right. Yeah.
Did you grow up there?
Yeah. I was born in a county called Yorkshire, and grew up. Spent the first 10 years of my life in a small village called Haworth, which some people may know because it's where the Bronte sisters are from. So, for example, they wrote novels like Jane Eyre, Wuthering Heights, which in a lot of school syllabuses. So
did you have to read those growing up?
No, I did actually read Jane Eyre while I was at university because I thought I really need to.
Yeah.
Just so that I can say that I at least read one.
What did you study in university? Was it related?
Oh, no, not at all. I studied chemistry, specifically medicinal chemistry. So when I got into my master's year, I focused on using novel organocatalysis. So green catalysts, ones that don't use noble metals or sort of toxic metals, really for building molecules for use in pharmaceuticals.
Wow, that sounds extremely complicated for an undergraduate. That was an undergraduate degree, right?
That was undergrad and masters. In the UK, we do it a little bit differently. You can choose to do like a combined undergraduate and masters. So it's like one long thing as opposed to the sort of 3-year undergrad and then having a master's separately. They're just together in a lot of cases. Yeah.
How did you get into that? Were your parents chemists or in that sort of field?
No, not at all. It really came from high school. I was very lucky to have a couple of very good chemistry teachers. One, in fact, won the National Science Teacher of the Year for the UK in the year that he was teaching me. So I remember we even had the whole film crew from the BBC round to our school to do a little sort of a few videos for the award ceremony, which was, on TV. That was really cool. That was my first taste of being on TV, I guess.
Yeah, you were taught by a celebrity. That's pretty cool.
Kind of. And then in my second year at school, my chemistry teacher, equally as inspiring. Actually, he works in the same company as me now. So I kind of followed in his footsteps. So that's really nice. And I bump into him from time to time at work. So
yeah, wow, that's pretty amazing. And so how did what you do in your undergraduate and your master's connect to your work now at National Nuclear Laboratory?
It's purely in the sense that it is chemistry. So I study medicinal chemistry. So it's a lot of organic chemistry, whereas more of what I do now is towards the physical and the inorganic chemistry. But I guess I always imagined that I'd go into something like pharmaceuticals. As part of my degree, I did a year in industry and I worked at GlaxoSmithKline on a pharmaceutical manufacturing site in the south of England. And that was very much sort of providing analytical support, quality assurance labs, so making sure that all the pharmaceuticals that they produce are to the correct standard, correct quality, that kind of thing. But I really didn't have any thoughts on nuclear at that time going through university. And after university, I almost did a PhD. But it all fell through at the last minute, and I'm kind of glad because I don't think, looking back on it, I wasn't quite ready at that time to do a PhD, and I think I would have just fallen into it rather than really wanting to do it. So I actually one of my high school buddies got in touch with me and said, "There's a job in the lab at the sugar factory where I work. Do you fancy it?" And so I thought, yeah, why not? So I went and worked at British Sugar for a year.
Doing what?
Working in the analytical laboratories. So part of it was providing plant support. So the guys running the various stages of the sugar processing sugar processing plant, they would ask me to get data, take samples periodically so that they can understand what actually is going on with the system, what state is it in, how close to being ready is the sugar, basically. But part of it was also a bit about continuous improvement. So running different trials on some of the different systems and providing that chemistry support to see, is it working or not, that kind of thing. So that was my first taste of getting up and close to an industrial scale facility.
Yeah. Yeah.
And just being able to touch it and hear it and hear and kind of get a feel for what's going on. Yeah.
Did you decide then that was your setting? You were going to be more, in big industries and working on manufacturing analytics?
Yeah. I guess it just gave me a really nice feeling that the work that I could do in the lab directly impacted a product and something that, was going into the supermarkets. And the work that I did, I could see how it fit into getting the product from its raw material, the sugar beets, and into those bags in Tesco, so to say.
And how long did you work there for?
I just did a year because it was very much, I just went into it because I had nothing to do at that point, because I decided not to do a PhD, and it all happened very quickly. But I used that time to figure out, okay, what do I want to do? And still, nuclear wasn't really on the cards.
So what were you thinking? What were the different things that you were juggling that you thought maybe I'd want to do this or that?
Well, it was mostly pharmaceuticals. And I think I probably applied for about 5 or 6 different pharmaceutical graduate programs. And didn't have much luck, if I'm honest. But then one day my mom called me and she said, you do know that Sellafield, that big nuclear facility that we live next to, they have a chemistry graduate program. And I took a look on their website, and it was about 3 days before the deadline for applications.
Wow.
So I just, I got my head down, submitted an application, and the next thing I know, I'm working there.
So for the US listeners, what is the Sellafield site?
Yeah, so I guess the equivalent in the US would be Hanford. Not that I know much about it. This is just what my colleagues tell me who've been to Hanford. But it's very much, my understanding is that Hanford is spread over a very large area, like hundreds of square kilometers, possibly. Someone might correct me on that. But Sellafield is like all that condensed onto about 1.5, 2 square miles worth of land. And it basically it's where the birth of the UK nuclear sector really was. It's where, we started building the early plants to get plutonium for nuclear weapons, because this was back in the 1940s when all this started. And then they went on to build the first ever commercial scale nuclear reactor in the world on the Sellafield site.
Wow.
And I think that was completed in 1954. And since then it is, it's evolved as a site. It's where the UK's nuclear fuel reprocessing plants are for recycling nuclear fuel, and where a lot of the sort of waste from the whole UK nuclear fleet is stored. So a lot of pond facilities, that kinds of thing. But now it's very much getting to the end of its reprocessing life. It no longer has operating nuclear power plants, so it's very much a site that needs to be decommissioned, but it's going to take a few years because there's some complex challenges.
What does it mean to be at the end of its refueling life?
Basically, the reprocessing plants that we have done all the contracts that they said they would. They've processed all the fuel that they need to. There's none left to reprocess, basically. So, there's no, yeah.
Uh-huh. So is that because you guys used to basically recycle fuel and now you don't anymore?
In short, yeah.
Why did that happen?
That's the UK's strategy, I guess. I think so we have two reprocessing plants. The first one is the Magnox reprocessing plant, which is to reprocess all of the fuel from our first generation nuclear power plants in the UK. And that's due to finish around 2022, I think, around about that time. And then the second reprocessing plant that we had is called Thorpe, Thermal Oxide Reprocessing Plant. And what that did is that reprocessed fuel for the UK's second generation of nuclear reactors, the advanced gas core reactors, but it also reprocessed fuel for overseas customers. So Germany, Switzerland, Japan, probably some others. But that was at a time that this was all sort of built and in the 1970s, 1980s, when uranium was a lot more expensive to purchase as a raw fuel. So it made sense to reprocess the fuel because, when a fuel rod has been in a nuclear reactor for 4 years or so, it's still about 96% uranium. So there's still a lot of useful fuel there. So it made sense to extract that and use it again. Now that the uranium price is a lot lower, it doesn't make economic sense to reprocess the fuel anymore.
So instead, you guys are just storing it at that site? But you said the whole site was going to be decommissioned. So where would the spent fuel be stored now?
Yeah, so we currently don't have a facility to store it in the long term, but we're seeking as the UK a site for a geological disposal facility, much like a lot of other countries are doing. So the intention is that all the waste will be homed in there.
Do you know if there's like a deadline of when you guys are trying to find it by and what the progress on it is?
So the new siting process was recently launched at the back end of 2018, and they've put together a nice plan of rough timescales as to, well, first finding a site, a community that is willing to host this facility, and from memory, I think that could take up to 15 years or so.
Wow.
So it's very much on a volunteer basis, following very similar to what they did in Finland, in Sweden. So once we find a site, I guess we'll go from there. I don't know how long these things take to build. We'll see what the Finns do.
Right. And so you applied 3 days before the application closed. Did you get the position?
I did. I think very much because I was a local boy, because I grew up close to the site. What I forgot to say is that after I spent my first 10 years in Haworth, in the Bronte country, I then moved up to Cumbria, which is where the Sellafield site is. So I spent my sort of teenage high school years living within 20-minute drive of Sellafield.
Did you know what it was when you lived there? And were you aware of it?
Yeah, my stepdad worked there.
Okay.
So he used to tell me bits and pieces, tried to get me interested. He's an engineer,
Yeah.
engineer. I think at that point I was probably more interested in playing PlayStation and going out and playing football. But maybe it worked in the end.
Yeah.
Yeah. What was I saying? So yeah, I think partly because I was a local person, and one of the challenges that they face up in that area of the country is keeping people in that area, especially young people who have degrees, because it's very quiet. There's a lot of mountains. It's very beautiful area, and a nice place to grow up. Feel very grateful that I got to grow up there. But there's not much to do unless you like walking, cycling, outdoors, that kind of thing. So I think a lot of people move there for their graduate program to get skills, get experience, but find maybe I need something a bit more lively, a bit more exciting. From the outside of work perspective, obviously the work is, there's a lot of really, really exciting challenges there to work on, unique challenges. So I think because I was a local boy, they saw me as somebody that, they could rely on to stay, and who knew the local area, who was sort of embedded within the local culture, I guess.
Yeah. And then what was the program like? What did you get to do?
Yeah, it's a really, really good program. I feel very lucky to have gone through the Sellafield graduate program. It was quite a well-structured 2-year development course. So you go through with a cohort. I think there were about 25 of us that particular year. So, we got to form some really nice friendships, people who I know that I will sort of keep in touch with throughout my whole career, wherever it takes us all. But you just get that on the job experience. You go straight into a team, depending on your discipline. So as a chemist, I went into the nuclear fuel reprocessing plant technical team, and that very much revolved around providing operational and technical support to their plant. And this was so different for me, coming from pharmaceuticals and sugar manufacturing, where I could stand next to the boilers, or all the different systems, and touch them and watch them and see with my own eyes what was going on. Then I went to this reprocessing plant where everything is in cells or caves, they call them, and you can only look at them through a drawing, and you've got to trust that drawing's right, and you can only tell how they're behaving through the data that you collect, the chemistry data, monitoring pressures, temperatures, all this stuff. You can't actually see what's going on. So yeah, that's a great challenge, I think.
Oh yeah,
but I
big
did
adjustment.
definitely, I definitely missed being able to just go up to the tank and put my ear to it and figure out what's going on. So a lot of it was providing operational support, looking at trends and plant data, reviewing things like flow sheets, because you want to know at every point how much material you have, because you're putting you're putting material in there that you have to account for. You have to know how much uranium you're putting into the front end of your plant, how much plutonium. You need to know how much you're extracting out of the other side, because you have to account for that.
Right.
So it's very important that you keep track of that data and those measurements, so that you always know how much material you've got.
That's a lot of responsibility as a graduate student.
Well, I mean, obviously, I was in a team. I was in a technical team, and learning from a lot of guys. Some of the guys that had designed the plant back in the 1970s, and
oh wow,
learning from them was really an invaluable experience. But yeah, so there was the plant support side of things. But then there was also a research and development aspect, which was really nice because it put your mind, a different mindset you needed for that. It wasn't about, okay, what do I need to do today to keep my plant running? It was, okay, what do I need to do to make my plant run better?
Right.
So I was really lucky. I got the chance to do a very cool project. And this is where I had my first experience of what the National Nuclear Lab did, how they helped industry sort of to operate. So basically on the plant we had this reactor, and it was operating, but it was a bit sluggish. It was very old. It was sort of built in the 60s, and the guys operating the plant had a hard time with it. And we knew it was because of a specific plant component. It was this nozzle that basically blew hot air into a reactor. And this nozzle would get blocked up with the powder that was in this reactor. So we thought, could we redesign that nozzle? Could we make it better so that, these guys can just switch on the air and it does what it needs to do, and they don't have to monitor it?
Could you?
Sorry?
Could you redesign it to do that?
Yeah. So I was I got seconded into the National Laboratory as part of my graduate development program. So I spent 6 months there. And while I was there, what we did is we built a non-active version of this reactor. And we had these nozzles that we wanted to redesign. And what we did is the National Lab at that time had just got a brand new 3D printer. So we thought, why don't we use that to just make loads of funky nozzle designs, see what works best. And this was sort of my first taste of seeing how the National Lab sort of links into academia. And, it was my first, I could see how you do a sort of literature review of fluidizing air nozzles and different designs and stuff, and draw from that academic material and bring that into a sort of more applied type project. So we drew from that. We designed all these nozzles, and the great thing about 3D printing is that you just set them printing overnight, and the next day you've got all your components. Yeah. And we did like 20 nozzles overnight.
Wow. What were some of the differentiations that you made on the nozzle?
It was like orientation of the holes. So in the problematic nozzle, the hole was on top, so the air was pointing straight up. And when the air was turned off, the powder just sat down and blocked up the nozzle. So we put the holes on the side, so the air was blowing out horizontally. And then that prevented the holes from blocking up when they were switched off. But looking at different sizes, different shapes, different number of holes, that kind of thing, and we basically put it in a mock reactor, tested them all out, and we could narrow sort of 20 nozzles down to a couple of candidates that were really good. Now, this was what I think was really cool about this project, is that we weren't happy there. Okay, we got a couple of nozzle designs that we thought, okay, these are better, these are good, but when we put them into our mock reactor, we can see that the powder is moving, but we can't actually see how well it's moving inside because it's opaque, right? It's opaque, so you can see on the outside of this reactor the sand moving, but you don't know what's happening in the middle. So we worked with a team in University College London who could basically, they had this bespoke X-ray imaging facility where you could set up your reactor, X-ray it in real time. So there's like 72 X-rays per second. So it creates like a video. So you can see inside this reactor of sand, let's say, you can see inside that, you can see the formation of the air bubbles from the different nozzles.
It's amazing.
And that really told us how good the new nozzle designs were. Right. And we could quantify that because you can measure the size of the bubbles and the mixture of sand, the air to sand mixture, that kind of thing. So yeah, that was my first taste of the National Nuclear Lab, really.
Yeah, and it's super connected to academia. They're drawing on both the research and then actually the tools that they have to come together. Exactly. And the 3D printing was pretty new at the time, right?
Yeah, I think so. Yeah, definitely for the nuclear sector.
Yeah,
definitely.
And so then did you decide to work at National Nuclear Laboratory after that?
Yeah, basically. I thought, I've had a great time at Sellafield learning the more operational side, learning about how a facility operates and all the issues that you deal with on a day-to-day basis. And I thought, I'd like to move in a different direction, a new challenge. But there was also personal reasons as well. And I think it's important to balance your work life and your personal life, make them work together. At this point, my fiance, and now fiance, she moved from Japan to the UK to do her PhD.
Oh, nice.
To be closer together as well. But it was like the furthest away you could get from Sellafield. It was in the southwest of the UK, whereas Sellafield is in the northwest. So I asked around a bit. I knew that NNL, National Nuclear Lab, had an office down in the southwest. So I asked around, and there was a position available as a plant chemist. I thought that
sounds pretty fitting.
I could fit that bill. I applied, and a few months later, there I am.
That's great. The stars just lined up for you guys.
They really did.
A little bit of hard work and a little bit of luck.
Sure.
A little bit of persuasion from your mom and your stepdad to go into the nuclear field.
Exactly.
And what was NNL like once you actually started working there? What kind of projects did you get to work on?
Yeah, so I my focus there was on reactor chemistry and corrosion, but more from the nuclear power plant side of things as opposed to the reprocessing side. So it was a new field for me in a sense.
Yeah. So how are those different? I guess.
Yeah, I mean, in a reprocessing plant, you're dealing with nitric acid, you're dealing with uranium, plutonium, but in like a dispersed form, not as a fuel pellet. You're dealing with temperatures up to sort of like 50 to 80 degrees, depending on which part of the plant you're talking about. Whereas in a nuclear power plant, you're dealing with water, high purity water, but very high temperature and pressure. So for a pressurized water reactor, for example, 155 bar pressure, which is high, and 325 degrees Celsius. So it's a whole different thing. It's about trying to keep that system clean, to minimize corrosion. Whereas the reprocessing is just like a soup of radionuclides and stuff, which you're just trying to extract the different components from it, the uranium, plutonium, and then you've got your fission products that you take away and you sort of immobilize them in a glass matrix. So completely different, really. But but it's chemistry, so I, I kind of could learn, and it was, it's just nice to see a different area of the nuclear sector. So a lot of my work in NNL has been around supporting the UK's nuclear plants in terms of sort of training their water chemistry, corrosion, helping them with corrosion issues. But also, the really special thing about NNL is that it operates on a commercial model. So like any company, but it's owned by government, and so we make a profit every year, and the government says, well, we'll let you reinvest that profit back into your facilities, back into training your staff, developing, the expertise, the strategic nuclear expertise for the UK. So as part of that, NNL has a series of funded research projects. And I lead one of the projects on hot water chemistry corrosion. So basically, nuclear power plant coolant chemistry. And what we recognized is that in the UK, we have a lot of different options on the table as to what kind of nuclear reactors we might have in the future. They could be your standard pressurized water reactor, boiling water reactor that we have elsewhere in the world. But there's also various small modular reactor designs, advanced modular reactor designs, advanced nuclear technologies, fusion, many of which incorporate water coolant circuits. So it's very much thinking about, okay, from a UK perspective, as a national lab, we should be investing in developing expertise in this area. We already have a lot of expertise in some of our universities, for example, Manchester, and other companies like Wood Group. But I think most of their work is done on non-active facilities. And what the really unique selling point of the National Lab is that we can work with highly active material. So the idea is to sort of build some capability for the UK in active hot water flow facilities. Yeah.
Yeah. And so you're studying how to prevent or minimize corrosion.
Exactly.
And how do you do that?
So there are various things. Different reactors designs have different methods. So in your pressurized water reactor, you can basically just inject a lot of hydrogen. And what that does is that mops up all of your corrosive species.
Is this hydrogen as a gas?
Yeah, hydrogen as a gas, yeah. Because what happens is the water, as it flows through the reactor core, you have this radiolysis of water. So the water splits up into, H and O, and these O's are often corrosive species. So what we do is we inject more hydrogen into that water to basically recombine with those corrosive oxygen-based species. So it just kind of reforms them into water, essentially.
Interesting.
But you also, some places inject zinc into their coolant as a solution. And what that does is that modifies the protective layer on all of your surfaces and makes them more compact, makes them more dense, stronger, and more resistant against corrosion. Because on all of your surfaces, you have this nice protective layer because of the choice of materials that we use. But then if that's a PWR. If you look at a boiling water reactor, they have all sorts of other different techniques. They too will add hydrogen. But if you add too much hydrogen in a boiling water reactor, it increases the dose rates around the circuit and in the areas of plant that the personnel are. So you can only add a little bit of hydrogen before you get increased dose rates. So what they do is they inject platinum nano, and they are injected as a solution, but when it hits the hot water, it basically disintegrates into loads of nanoparticles. And those nanoparticles spread throughout your coolant system onto the surfaces. And those platinum nanoparticles act as a catalyst for your recombination of hydrogen and oxygen. So it means that you don't have to add as much hydrogen to mop up all of those oxygen or oxidizing species.
Is it safer to use zinc rather than hydrogen as well? Or does it not make a difference in terms of safety?
In terms of safety, there will be limits on how much of these things, like the concentrations of these species that you can have in your coolant, because once you get above a certain concentration, they're going to have adverse effects on some of your materials. Like, for example, on your fuel cladding, your zirconium, if you add too much hydrogen, you get zirconium hydride, it gets brittle. So, there are definitely safety implications there. So it's very much about, you've got all these different tools that you can use, and it's about optimizing them to find the right soup, so to say.
Yeah. So. Does this optimization happen just, let's say, before the reactor and the whole system is built, and then it's kind of kept the same the whole time that it's running? Or is it like a daily thing that you're looking at it and re-optimizing it, or hour by hour even?
Sure. I mean, there are guidelines that have been developed by the major sort of operating fleets. So in the US, you've got EPRI, who developed the chemistry guidelines, and they've been developed over decades based on plant experience, operational experience. So they're a really good set of sort of, a range of the different species that you should have in your coolant. They have these nice ranges, and you say, make sure you're within there, and things should be running pretty well, basically. So, yeah.
And then in terms of your guys' research at NNL, is there any type of reactor that you think that the UK will favor more towards in the future, that you're sort of focusing on optimization for rather than others?
It's an interesting time at the moment. So it's difficult to put all your eggs in one basket. I think at the moment we have to be prepared for many different types of reactors. We've had a few hiccups in recent times with some of the vendors pulling out. For example, the Koreans and the Japanese had plans for a new build in the UK. And we were starting to develop expertise to support those guys, to support those plants, but they've either been sort of mothballed or put on hold for now. So it doesn't. You've got to take that into account when you're thinking ahead. But the really nice thing is that there was an advanced boiling water reactor that is currently on hold to be built in Wales. And we started looking at the chemistry for that plant because it was going to be quite unique in that from the very start of the reactor operations, they were thinking of a chemistry of hydrogen, zinc, and platinum, which many plants in the world operate using that chemistry, but they haven't done from the very start of their operations. So we started to build up some capability looking at particularly platinum nanoparticle injection. But when the project sort of got halted, because we couldn't find the right funding model between the UK government, Japanese government, Hitachi. It seemed like a really bad thing for our project. But the really nice thing is that we link in well with the Fusion lab in the UK, and they are looking at water coolant circuits for the demo fusion facility, which is the one that will come after ITER, which has been built in France at the moment. So we can definitely, we've got a really nice program of work now looking at transferring that knowledge, that experience in water chemistry and corrosion from fission plants, so boiling water reactors, pressurized water reactors, to these coolant circuits that they're still designing for the demo fusion plant. And it's so cool. There's so much going on. There's so many funky conditions going on in that fusion coolant circuit.
Yeah, tell me about the fusion coolant circuit. How is it different than the fission, and what's so cool about it?
So I guess the first thing is that you have higher energy neutrons in a fusion reactor. Sorry. So
it's okay. It's bound to get it wrong once.
I corrected myself. You have these really high energy neutrons, which you don't have in a fission reactor. And what that does is that will have an impact on the material itself, because you've got these neutrons bombarding the material. And what they do is they knock atoms out of place within that material, and that can lead to all sorts of things. It can lead to cracking, that kind of thing. So we need to understand how these higher energy neutrons, what impact they have on the material itself. And there's a lot of work being done around the world on that at the moment. But also what you've got to do is you've got to understand how the neutrons affect the water in the coolant circuit. Because as I said before, the neutrons split hydrogen and water. If you've got higher energy neutrons, are you going to get more of that splitting? So therefore, are you going to have to inject more hydrogen to make it recombine into water? So we need to figure that out. But then the other thing is that you have these high magnetic fields up to 10 Tesla, and that's what the coolant parts of the coolant circuit are exposed to. And what we need to understand is, how does that magnetic field impact the formation of that protective layer that you want to build on all your surfaces to help mitigate corrosion? Is that magnetic field going to weaken that? Is it going to make it unstable? Is it going to strengthen it? You have magnetic fields in different orientations. So do you need to orient your coolant circuit in a certain way to use the magnetic field as a good thing, or is it just going to be a bad thing altogether?
Right.
So this is something that we're starting to look at.
How do you even study that? What would an experiment look like?
Well, you just set up a rig in the lab and get a magnet and put some samples within the magnetic field and put them within the high temperature water coolant loop. See what happens.
So it's like a very mini system.
Yeah. You're building a little mini fusion system in your lab, but without the fusion. just the high temperature water, the magnetic fields, and the right materials. This is the other thing, is that they've developed these new materials for use in the fusion reactor. So we don't have experience of of putting these in a coolant circuit and seeing how they interact in that environment of the high temperature pressure coolant in the magnetic field. Do we need a different type of chemistry for these new materials to make sure that they can withstand this pretty harsh environment? So yeah, it's all stuff that we're sort of slowly tinkering away at, but it's really exciting.
Yeah, you said slowly. What's the timeline for this commercial fusion station?
I think at the moment, the demo, which is really going to be the blueprint for what a commercial facility would look like, they're expecting to build it through the 2030s, 2040s.
Okay.
I think that's the current timeline.
It's pretty soon for fusion.
Yeah. I guess it'll depend how well the ITER project goes.
Right.
So fingers crossed. Yeah. but it's nice to have that kind of goal to align with in your sort of early to mid career, because you're like, okay, that's within my lifetime. I can genuinely have an impact here and hopefully help make that happen, right?
Right. Yeah, it's amazing how you went from hardly a background in nuclear to knowing, down to the atomic level, like what is happening in the nuclear plant. It's a big... So how long have you been in the industry? Like how long have you worked at
NNL? 4 years at NNL.
Okay, so
my 4-year anniversary in 5 days.
Oh, congrats ahead of time. Do you have any celebration planned?
I'll probably have to take cake in or something.
Yeah.
and everyone was, why are you bringing cake?
And I want to talk a little bit about your involvement outside of NNL, working with the young generation. How did you get involved with that? What was sort of your inspiration to start working with the younger crowd?
So I guess this all started basically when I joined NNL. I had just finished the project on redesigning the nozzles with 3D printing. And when the Nuclear Institute Young Generation Network rep in NNL sent out an email to all the young ones saying, we've got a Young Generation Network issue of the next journal, the Nuclear Future Journal that the Nuclear Institute publishes. Do you have any projects that you could write up into papers? And I just finished this nozzle project and I was still really excited about it. So I thought, I'd love to write that into a paper. So I wrote that with some of the guys at Sellafield and at University College London. And 6 months later, that was, it was published. And, that was a really, really nice feeling to get that hard copy of your paper. And that was my first taste of authoring a paper. And then kind of out of nowhere, I got this invitation from the Nuclear Institute to attend their annual dinner in London. And I'd never really heard about it before. And I just thought, oh, they're inviting me because I wrote a paper and, it's they're saying thank you. So I thought I'll go along. And it wasn't until I got there that they invited me because they awarded me the Pinkerton Prize, which is the prize for the best journal paper that year published in their
That's
journal.
An amazing surprise.
So yeah, and it was, I turned up and I remember that moment of going to my table, seeing my name and seeing Pinkerton Prize next to my name. And I thought, what's Pinkerton Prize? And, some of the other guys on the table knew. And it was just a really nice feeling.
Yeah.
So that kind of led to, I guess, to me being invited to be part of the editorial committee for the Nuclear Future Journal. And as part of that role, I coordinate all the input from the Young Generation Network all of that, the articles and stuff, and every 2 months gets published. So
you get to actually go through and read them.
Oh yeah, and critique them as well.
Yeah.
But it was a really good time to get that role because it was a completely clean slate. Because the Young Generation Network, the year before I joined in that role, they were so focused on delivering the European Young Generation Nuclear Forum, ENYGF, European Nuclear Young Generation Forum in Manchester. So they'd not had as much time to focus on the journal content. Mm-hmm. So it gave me a clean slate. So I thought, okay, what do I want to do with this? It's an opportunity to do what I think is right for the Young Generation Network in the UK. So I kind of put a bit of a strategy together with a few buzzwords, and but they're around. So the first one is around participation and about individuals engaging with the journal. So I wanted it to be more than just a magazine that they picked up every 2 months and had a quick flick through or whatever. I wanted young people to be connected to it as individuals. So we started running these opinion polls, asking the young generation of nuclear workers what they thought on various nuclear topics. And, so every 2 months they could fill out the 5-minute survey, and then in the next issue they'd see the results, and, both qualitative and quantitative. And we would just write them up into little articles. So that's the first thing I wanted to do. The second thing was about celebrating successes, raising awareness of the really good work that young people are involved in, spreading these good stories. So what we do is we do Q&A articles with, people that we come across that are doing some really cool work. For example, I've just done one with a PhD student of ours at Bristol University who's using like really novel surface imaging kit to interrogate, the surfaces of nuclear materials. And I thought that's a nice story to tell for a young person, pushing the sector forwards, really.
Yeah.
Then the third thing was about education, about so to kind of achieve that, we do these Mythbuster pieces where every 2 months we pick a common myth, a common misconception about nuclear, and we bust them. But what that does is it gives the reader some information and some background which they can use in their conversations if people ask them about these topics, whether it's about nuclear waste, whether it's about public perception, whether it's about the environmental impact of radiation, all these things. So yeah, it's about giving our readers some tools that they can use so that they can themselves develop into more effective communicators and ambassadors for the nuclear sector.
Right.
And the last one is, I called it imagination. And it's really just about giving young members of the nuclear workforce a platform on which to express their ideas and their thoughts. So, they can do this through opinion pieces, that kind of thing. If they read a recent report from somebody, what did they think about it? What are its implications for nuclear and going forwards? So yeah, that's what I'm sort of aiming to do over the last year or so. So we'll see. That might evolve a bit as we go forwards.
Yeah, and just as we wrap up, from everything that you have learned from them and from your role as a plant chemist, what do you hope for the future of nuclear? What looks like some really cool emerging technologies?
One thing that I haven't mentioned yet, which I hope I could quickly mention, was...
This is all about you?
It was about public perception and public engagement, and because that's another really big piece of work that I'm involved in, because I think that's one of our biggest challenges as a sector going forward, about this social license to operate and the way in which we interact with society at large. I think we could improve a lot as a sector in this area. So when I joined NNL in 2015, I heard that we had an internally funded R&D program on public engagement. So I straight away got involved in that. And now I lead that program, which is really nice. I guess, we've done a lot of work over the past 3 years looking at research in public engagement. It's not been about doing public engagement. It's about figuring out how to do it better. And when I talk about public engagement, it means every kind of interaction that the nuclear sector has with society. Because I often ask people, when I say public engagement, what do you think? And you get all sorts of answers. Right. And the great thing is that they're all right, because they're all examples of the way that society and the nuclear sector interact. So we've done various things, like we've done public dialogue studies where we get a group of 20 members of the public, and we sit down with them for a weekend, and we go into a lot of depth as to what they think about nuclear, and specifically the way in which they want to engage with the nuclear sector, and by spending quality time with members of the public, you can really extract a lot of really meaningful information, which we can use to inform the way that we engage, and make sure that we can develop more nuclear ambassadors, more effective communicators in the sector. So that's like one thing. That's the finding out how to do it better. But then you've got the methods for how to do it and how can we improve those. So public consultation, for example, if a new nuclear reactor is going to be built in just down the road, you might have somebody coming around on your door and knocking on your door, and they want 10 minutes of your time to ask you a few questions about what you think. But those questions are usually predetermined. It's about what the industry wants to ask you about. And you might have just got out of the shower, you're all flustered, and you're just not in that space to talk about the UK's nuclear sector and the plant that they want to build 10 minutes down the road. So what we want to do is develop methods for public consultation that are more meaningful, that are more inclusive, and so one of the things that we've been working on with Manchester University is they've got this network called the BEAM Nuclear and Social Science Research Network. And what it does is it brings current social science thinking into nuclear practices. So that when we're engaging with society, we can do it a lot more effectively.
Right.
In an attempt to build trust between the public and nuclear sector. But what I see in this new technique called hybrid forums that we've been trialing as a way of conducting public consultation at a local level. What it does is the aim is to create local ownership of a facility. So you might have a small modular reactor, and what the aim is that rather than that community feeling like the nuclear industry is doing this to us, putting this small modular reactor in our community, it's more about the community shaping that small modular reactor, shaping how it looks, how it operates,
right,
and everything around it, so that it's their facility, so that they have ownership of it, and they're proud of it.
Yeah. Right.
Ultimately, that's what we want to get towards. And in doing so, you can build a lot of trust between the sector and society. And yeah, so that's a really nice thing that we're working on. But I think, to answer your question, that's one of the biggest challenges that we've got going forwards. And if we don't get that right, I might not be able to do all my reactor chemistry, my plant chemistry, because there'll be no reactors left.
Right. Yeah, well, I think that definitely getting the public to give their opinions and be engaged in it before they just put nuclear in somebody's backyard, that'll help show people, and hopefully shows like this will help show people that nuclear is actually a really great solution for our energy problems, and that they'll probably themselves become titans of nuclear, and slowly we'll have more and more plant chemists.
Hopefully. I mean, the really powerful thing that I learned from these public workshops that we did is that at the end of the 2 days, these people who, honestly speaking, they told me they didn't even know there was a nuclear power plant 50 miles away and that there were plans to build a new one, because they were a non-nuclear community. They had no history of it, no awareness of it. At the end of those 2 days of quality time, where we had open, honest conversation, they said, can we be a group of nuclear ambassadors for our town? Because we've really enjoyed these 2 days. We really appreciate it. And we want to spread the good word about nuclear because, actually, we think it's a good thing. So it just showed me how powerful that one-to-one interaction and taking that time to do meaningful dialogue and conversation, the power that has.
Yeah, absolutely. And on that note, Reuben Holmes, thank you so much. It's been such a pleasure.
Thank you.